Kia ora tātou, it's Bill here. I want to have a look at bitwise operators today and these Boolean identities covered before. So let's have a quick roundup of these bitwise operators: a single ampersand for an AND, single bar for an OR, this caret symbol here for an inclusive OR, the tilde squiggly line there for one's complement, double less than here for shift left, and double greater than there for shift right. We are not looking at these double symbols here, double ampersand, double bar, which are used for truth and falseness of values and variables. We're looking at these bitwise operators that operate on one bit at a time in a register. Now, the Boolean identities, if a bit in a register, we don't know what value it is. If we OR it with a 0, then it remains the same. If we have a bit in a register and we AND it with 1, then it remains the same. So if it's a 0, we AND it with 1, it stays 0. If it's a 1 and we AND it with 1, it stays as 1. However, we also have these which force the bits in a register to either a 1 or a 0. We make good use of these. So if we have an existing bit and we OR it with a 1, then whatever the bit was is lost, it just becomes 1. And the bit that we have, whether it's 1 or 0, we ampersand AND it here with a 0, then we're forcing that bit to go to 0. We're going to make use of these today. I want to do it in the context of this countdown timer that I've got here, and it's got a variable countdown opportunity. So at the moment, I've got the value 5. I can use this switch here to increase and this switch here to decrease the values. Just find my pencil, I can press these buttons. So if I want to increase that from 5 to 6, I just press this, that's 6. Press it again, 7. If I press it again, it won't go above 7. If I press this button, it decreases. There we go, 5, 4, 3, 2, 1, and it won't go below 1, okay? So let's just increase this to say 3. And what I'm going to do now is I'm going to push the start button, and it's going to count down from 3 to 2 to 1, and then when they've all gone off, there'll be a double beep. There we go. And of course, when it's finished, the original number comes back on the display again. So let's just change our number again to say 5, 6. Let's change it to 6, and then we'll start our countdown again. 6, 5, 4, 3, 2, 1. Double beep, and it displays the 6 again. Now, I'm not going to go over the operation of this code at the moment. What I'm really interested in is we've got this value, 6, and we have to put it onto these LEDs. So how do we do this? And we're going to make good use of our bitwise operators to do that today. Let's have a look in our code. If we go to the simulator, you can see I've got a function there, show count, and what it does is it takes a value and it shifts it left by 1 and puts it onto port B. So it's having a little explanation of what's going on here. Here's port B. Port B has got 3 LEDs on it. Okay, so let's think about this. We've got 3 LEDs on port B. Have a look at this piece of paper here. Here's our hardware register port B. We've got an LED here, we've got an LED here, and an LED here. And at the same time, we've got a variable called val, which is a single byte in our static RAM, and it has the number 6 in it. And what we want to do is we want to put the number 6 onto these 3 LEDs. Well, actually, that's quite straightforward, because what we do is we just shift this left and pop it up there. This 0 then goes into here, and this 1 goes this way into here, this 1 goes this way into here, and becomes 1. And then we write that to port B, and we end up with our circuit. And it works really fine, doesn't it? Well, actually it works fine, but there's a huge problem with this. Because what we've done at the same time as actually shifting this left and popping it up into there, what we've also done is we've taken this 0 and we've put it into here. And we've taken this 0 and put it into here, and this 0 into here, and this 0 into here. And this 0 falls off the end, another 0 comes in and gets popped into there. So what we've done is we've actually forced these other bits to 0. Now, in this particular instance, it works fine. But why? We're actually forcing these other things to 0, and maybe we can get away with this in this instance. Well, let's have a look at the schematic. Sorry, at the layout of the board. We've got other components on this board. They're not playing up. Well, they don't appear to be. If we have a look at our simulator here, what we've got is we've got our 3 LEDs on B1, B2, and B3. We've got a switch on S3, switch S3, which goes to B4. We've got nothing on B0, nothing on B5, and there is no B6 and 7 on an 80 mega 328p. So the reason this works in this instance is because I'll draw your attention to my 4 switches here. What I've done is I have added pull-up resistors. I think I've used 15k resistors here. Yep, 1, 5, 0, 2 zeros. So I've used 15k pull-up resistors on here, and I'm not using the internal pull-up resistor. Well, that's actually quite important in this situation, and allows me to get away with this naughty thing that I've done here with this line of code. Now, when a pin is configured as an input and we want to turn on the pull-up resistor, what we do is we write that particular bit in the into the output register port B. So if I want my switch, which is on B4, when one of my switches is on B4, if you look at it over here in the simulator, B4, we've got a switch on B4, and it is the third switch. Switch 3 is on B4. So I can get away with this at the moment because I'm using the external pull-up resistors and not the internal ones. But if I decide in the future that maybe I want to change from using external pull-up resistors to the internal pull-up resistors, then this value here I can't write it to 0, because what will happen then is it will turn off the internal pull-up resistor. And also, what if I decided in the future that I wanted to connect something to B0 in my simulator? There's nothing connected to it. And the same with B5, there's nothing connected to it. But what if I wanted to connect something to that? I can't afford to write a 0 into bit 0 of port B, and I can't afford to write a 0 into bit 5. And now also in the future, say we wanted to change this software to run on a different AVR microcontroller that actually had bits 7 and 6 here of port B available to us, we could try and use those. But I'm writing 0 into that. We cannot do this. This is not how we do bit manipulation. We do not just overwrite the whole register. So how do we do this accurately? Well, the little process that we use is fairly straightforward to follow. The first thing we need to do is we need to turn off the bits we want to use in the register, leaving the others the same. So that's the first thing we want to do. We just want to turn these 3 off. And then what we want to do is take this and only copy into it the ones that we're interested in. And there's some very swish code for doing that. Let's have a look at, in our program, you'll see that further down, I've actually got a good show count function down here, right? I'm going to copy what's in that function. I'm going to put it into my simulator. And now you can see what happens is, what I'm doing here is I am forcing just these 3 bits to be 0. If I look at my my Boolean identities, if I AND something with 0, I force it to 0. If I AND it with a 1, I keep it the same. So that means here that port B is getting forced to 0. Those 3 are getting forced to 0. What's the effect of that in our program? Let's step through our program. Where are we? There we go. Step. There's our internal pull-up resistors getting activated. Our initial value of count, and here's show count. We're going to jump down here, step. This thing is it. What it's going to do is it's going to turn off those 3 LEDs. Oh, I've jumped straight to this line here, and it's turned on the particular LED I want. Let's run our code for a bit, and we'll just increase the count value. There we go. Now we're going to go into step mode. So I'm going to decrease my count value. There we go. I've now decreased my count value. It's gone back down to 4. It's still showing 5 at this stage. We haven't got round to the code at the moment. And better release the switch. And now it's going to show it. Now you can see what's happened here is that at the moment I've turned off all the LEDs, and LEDs have all gone off. And the next line of code will turn on the LEDs that I want. There we go. Now you'll notice that in my program what's actually happening here. And you may have noticed this, and it may be in your mind as to when the program was running, what was going on. The program's running at the moment. When I press the switch, the LEDs get brighter. When I release the switch, they go back to dim. Okay, and that's what's happening here in this line of code. Here is I'm turning off the LEDs and I'm turning them back on again. And so my LEDs are actually flashing on and off at the moment. But they're flashing on and off so fast that we can't see them. They just appear to be dim because they're actually turned off for one instruction period here, whatever this period of time is, which in a microcontroller running at 16 megahertz is not very long. But then this doesn't take long either, and neither does this other loop. So the LEDs are actually flashing on and off at the moment. And that's why you see in this demonstration here that the LEDs dim when I go brighter when I press the switch, because when I press the switch, they're stuck in a holding pattern and they're not being dimmed. Just something in case you wondered about that. Anyway, so now we've got this piece of code. What's it actually doing? What I've done is I've also created a function called expanded show count to show you exactly what's happening here. And I'll copy this in. There we go. So what's happening is the first thing we do is we grab a temporary, we create a temporary variable, and then we copy port B into the temporary variable, and then we AND it with this amount that we want, which is going to force these 3 bits to 0, and then we write that to port B. So this line of code down here in line 173 here, which is our single line of operation, what it does is it creates a temporary variable. You can't see that in here, but it creates a temporary variable, changes the value of the variable, and writes it back into the port. And then what it does is it comes down here and it creates a temporary variable for our value, which has come in, and then it shifts it left, and then it writes that into the port. But because I've got that wrong there we go, there's a little bug there. That needs to be ORed. There we go. Now that's correct. Sorry about that. Put that in. Why is that not going there? There we go. It's in there now. Keypad. So what it's doing then is it's ORing it with the value that's already in there. And this will put the new value in to only the register bits that are involved with these 3 LEDs and keep the others the same. Now, scratch your head a little bit. You might be able to think of a way that you could make this different so that the LEDs weren't dimmed. Anyway, that's something for you to think about. As an extension to this, I want to have a look at the actual code and show you what's happening in the assembly code. Now, this is extra. This is not something that would be part of any assessment. So what I'm going to do there is let's have a look at our countdown function. Here it is. This is what's going on here. But when we turn this into machine code by compiling this, we'll have a look at what actually happens. So if I open up the output files, I'll find the actual compiled code in main.lss, and I'll open that and I'll look for my show count function. Here it is here. Here's show count. So as I said, this is an extra, and it won't at all be assessed, because now what we're looking at is we're looking at the machine code to see what actually this line of code turns into these lines of code when it's assembled. And so what happens is that these numbers 95B1, 917F, 95B9 are written into the flash of the microcontroller. Remember, it's this machine code which is written into it. This C code is compiled into machine code. But there's an in-between process, sort of semi-readable code called assembly language. And so what this assembly language is then converted into this machine code. And this command in means take the value 5 and read, well actually, no. Take the address number 5 in our microcontroller, which in our address 5 corresponds to port B, and drop it into a temporary register R25. This is a bit confusing, but just to help you, what I've got is a piece of paper here where I'm going to lay this out for those of you who are really champing at the bit to understand this. So port B has actually two addresses. It has the address 0x05 and 0x25, and it depends on which assembly instructions you're using as to whether you use this address or this address, and the in instruction uses this address. So whatever is in port B at the moment is then copied into one of our general purpose registers in memory, and we have 32 of these. And so what's happening over here in this is we're taking what is in 05. 05 is our port B register, and we're copying it into R25. So R25 is just one of our registers. So that takes whatever's in there and copies it in there. And then what we do is we AND it with our number 0xF1, which is of course this number here. And so whatever we copied from port B, we've ANDed then with our masking number here. And then what we do in the next command is we take what's in R25 and we take it out and we write it back again. So over here in our assembled code, you can see that. And there's a very similar process here. This is an interesting little thing here about compilers for some of you to follow. Now what happens here is we take our value of port B, we stick it into R25. So we grab our port B value. Then what we do is we take our value that's in R24 and we add it to the value that's in R24. This is the shift left operation. Now, let's just think about this. Shift left is actually a multiply by 2, which means that if we add what's in R24 to R24 and stick it back in again, we've actually doubled it or shifted it left. So this is an interesting little thing that's happened in our compiler here, is we've changed a shift left 1 to an addition. Interesting. Then what we do is we OR it with what's in R25, and then we write it back out to port B again here. Cool. So this, and then we return from our function. So this is the assembly and machine code instructions that are unpacked from our C code. I just wanted to show you this to give you a feel for what's going on. Excuse me. And this bit about machine code is just for your general understanding. It won't be assessed, of course, but it helps you understand that one line of code here could be several lines or several operations within the microcontroller. Here, it's this line of code becomes 3 operations. This line of code becomes 5 operations. Well, 4 operations, and then there's the return. Just to show you that. Look, I know this is complex stuff. But it's really important to take away from this something that you understand, and that is that you